Okay, we're good. All right. So, hi everyone. I'm Sinead. Should I be pointing at?
It's not working at the moment.
Right.
The
Okay.
window is not working.
Sure.
I'm trying to set this pointer, but it's blocked by the panel.
Okay. Right. So I'm I'm doing a PhD on climate responsive systems as part of the wider EU program on solutions for outdoor climate adaptation, and that's an industry-based PhD separated into three research focuses on vegetation, water, and the climate responsive systems at both the city scale and the street scale. So some of my colleagues are actually presenting in the next few days, so you'll get kind of an overview of the program. And my particular partners were the University of Kent in the UK and Carlo Ratti Associati, which is a design studio in Italy. And being an industry-based PhD, it was kind of framed around a design problem as well as a research question. So I was looking at heat stress, which is an interesting design problem because it is an urgent global issue, but it is highly variable at a local street scale. So design solutions can really have a big impact here. And in particular, solar radiation is, as we know, one of the strongest impactors on heat stress, which is very variable. Looking at this picture, you can see even from 1 meter to the next. So solutions need to be very adaptable, but also scalable to have an actual wider impact on the problem of heat stress, which already leads me to the idea of temporary shade strategies and investigating how to create a climate responsive shading strategy for urban environments. And through that kind of design problem, I'm also researching better how to connect microclimate science and design. So there's kind of a twofold, looking at the process as well as the actual prototype that comes from this. And rather than looking at climate responsive design as a technological solution, which quite often comes up in like adaptive facades or even bioclimatic vernacular architecture, I took a systems or ecological approach, looking more at the connections and the feedback loops that are created in a way systems can respond at different scales. So that kind of looks like this rather complex or complicated looking map. This was the start of me trying to sort out all the different effects just a simple shade strategy might have on thermal stress and what's feeding into that. And one thing that map highlights with all these arrows is the importance of data in design for understanding all those connections and relationships. So a large part of my research was how to connect microclimate data and analysis into design, which meant looking at design-friendly tools and software, so open source, parametric, already used in design, such as Rhino and Grasshopper, which some of you may have come across. I was using Ladybug Tools, which is a free plugin for Grasshopper. And I had a lot to say on that, but actually what's relevant to this presentation is how important local microclimate data is in calibrating Ladybug Tools to provide accurate results. So this graph is showing a study of shading material measured versus simulated surface temperature. You can see the effect that a calibrated EPW has on the resulting surface temperature. And that table is actually a result of a mistake of mine in field measurements. I actually forgot to turn on my little Arduino setup to measure microclimate. All I had was the air temperature under the canopy. But what I realized is I could use that and Wallacey, which is an evolutionary solver. So it basically runs through the EPW days within the summer period to best match the measured and simulated results within Grasshopper. And what it gave me was actually a big improvement in the simulation results with just that one air temperature underneath the canopy. So that's actually very useful in terms of design where you might have limited data. So back to the actual prototype, back to the map. there was the three areas identified: form, material, and context for designing shade. I was really interested and zoomed in on material properties because of their multi-scalar effects. So something like reflectivity, which is affecting thermal comfort underneath, but also above the shade. So indoor, outdoor, and on a larger scale, the urban heat island even. And that resulted in me finding glass fiber, which most of you would know it's a widely used material, but there was an Italian sailmakers producing a glass fiber textile in a kind of 3D manufacturing process, and that was found to be retroreflective, so it's able to reflect the radiation back to its source rather than scattering in the urban environment. So with that property, I was looking at how can that be applied in the streetscape, remaining scalable but also adaptable to the local context. So it consisted of a structure, a simple, easily assembled, disassembled structure using standard materials. The glass fiber shade sails, and those were optimized, the position was optimized based on environmental analysis. So that's two iterations of that system, one in a public space, one in a private kind of street canyon style space. And at the moment, they're currently just positioned based on pulleys and these knots. They're fixed with these knots that represent the optimization for that particular month. And those knots are actually just determined by this grasshopper script, which is synthesizing a bunch of information that comes either from environmental data or talking to community members, things like what material is available and the location, the usage of the space. So that's just giving me the very simple measurements of where to tie those knots. And if we look in more detail at one of the iterations, this was built in a old tram line that got turned into a park in Turin, in the city centre of Turin, and that was built as a workshop with the community members and some students around. And the middle image is showing the digital, what was advised to me by my script, of how the sails should be set up, because the whole day basically was in need of shade. But what you actually see in the space is it's not used very much. There's very low numbers using the park, but it's also only in late afternoons and evenings, especially when events are managed. So that's an interesting one to consider. I'll talk about that later. And another point was I compared the glass fiber with HDPE, so high density polyethylene, which is common in shading materials. You can see, for example, both these sails have been left up for a few weeks over summer. One did a lot. The glass fiber did a lot better than the HDPE. But this thermal image is showing a higher surface temperature from the glass fiber, which at first thoughts you would think would have a negative impact on the thermal comfort underneath. But in a smaller scale study comparing these two samples, you actually have lower air temperature underneath the glass fiber, especially during the sunny periods, which are the unshaded. But you do have similar long wave temperatures. So it's the difference is how it's interacting with the shortwave radiation there for thermal comfort underneath. And on the microclimate study of both mean meridian temperature and air temperature, you see a reduction in air temperature. Those peaks in mean meridian temperature because of those gaps in the sails. And again, you see the improvement in simulation results when the data from that project was used to feed the simulations. And with that simulations, you can kind of carry on the design. So you see if it had been optimized for late afternoon, which is that image there, you definitely do have improvements in the hours when people are actually using the space. So two things that I could take from this is how to build the feedback loops back into the system, and that's again with data. So just having that air temperature to calibrate the grasshopper script so that you can actually, maybe this is a temporary structure in a space that needs development, but it can provide a lot of information for future design choices. And the other thing is data sharing, so making that data available maybe it's on an app and someone can look and see that's where the cooler area is, and that's the space I want to go and use. So you actually have this kind of continuous loop that continually improves the space in which the shade's located. And the other thing is the question of scale. So in the first point, in the factory iteration, there's very few angles that the shade needs to block. In the second, it's trying to do too much with too little. It was kind of failing at providing enough shade. And perhaps if you have a higher threshold or higher resolution of the structure, so an option for smaller cubes which provide a greater level of adaptation. For example, this is a prototype. I didn't get to test this, but this is like a mock-up of what it might look like. You can provide that extra level of response where it's needed. So if you zoom out and look at the system, it's quite a simple. So it's a simple strategy. It's just a unit with some sails in it. But if you kind of take that and build onto it with, for example, this matrix, looking at how it responds at different time scales across different spaces, and look at things like how this might differ in different climate zones, with different material properties, wind effects, because this can be vertical, so perhaps there is an option to put in wind simulations to look at also how to capture or avoid wind. So in conclusion, I think there was some really interesting there's very interesting possibilities for materials for improving materials in the urban landscape. Glass fiber was one of them, and I think that the connection between indoor and outdoor thermal comfort's really, really valuable to look at. The importance of data in design, and these parametric tools I was using were very rapid and accessible, so they really provide that feedback that you need to actually accurately design for microclimate. And climate response as a system that's not considering just the environmental, like the environmental conditions of the site, but also creating connections within the community, because that became really an important part of climate adaptation. So thank you, and I was lucky enough to have a lot of different partners involved. So.
Thank you, Sinead. So do we have questions for Sinead? Right up front here. And if you could repeat questions into the microphone for the recording.
Sure, yeah.